can have you.
Let's start. Yeah.
Okay, so let's
For those
start.
who don't know, today we have Frischippo, who is joining us from the CNRS in France, and he's going to talk to us about enhanced sampling and free energy methods.
Thank you, Raphael. And thank you for hosting this this workshop. So today I will talk to you about enhanced sampling and free energy calculations, and especially in the context of NAMD. So apparently I cannot, oh yeah, okay. So for those who are interested in free energy, in perpetual motion, and how to save money, this is not the right class. So what we're going to talk about is more like the real free energy, not the so-called Tesla perpetual motion free energy machines, which of course violate the first and second laws of thermodynamics. But the real free energy, and this person here, so you're going to see a lot of pictures. So on the left-hand side, this is Tesla, and this is Hermann Helmholtz. The free energy in the Helmholtz sense is the thermodynamic potential that measures the useful work obtainable from a closed thermodynamic system at constant temperature and volume. And of course, there is the equivalent, what you see here in the background, this is Gibbs, and the equivalent of the Helmholtz free energy would be a transformation done at constant pressure. But why is it important to study free energy? The reason is that any molecular process will proceed spontaneously if it leads to a net decrease in the Helmholtz or in the Gibbs free energy. So we better know how to predict how the free energy evolves to know whether a reaction will happen spontaneously. So I like to classify free energy calculations in two categories, and this is my choice. I mean, you don't need to follow this choice, but I like to consider alchemical transformations, and in the spirit of the old or the legendary alchemist transforming lead into gold. And we can do that because we have a potential energy function, and we can play with this potential energy function as we see fit. I mean, playing with the charges, playing with the van der Waals radius. And this is in contrast with geometrical transformations where you actually play with the Cartesian coordinates or possibly the internal coordinates of your system. So in one case, we're playing with the force field with the potential energy function. In the other case, we're playing with the coordinates of the system. And so with that, this is going to be my outline for the class this morning. So I will start giving you a brief introduction. Why do we want to do free energy calculation? What can we do with free energy calculations? And then following the classifications that I just mentioned, I will separate, or I will distinguish alchemical free energy calculations from geometrical free energy calculations. And finally, I will end with some concluding remarks and of course, questions. But you should feel free to interrupt me at any time. I mean, for some of you, what I'm going to say is trivial. And maybe for some of you, it will be a little bit arid. I hope not. But we don't want to have anyone left behind. So just stop me whenever. Don't be shy. Okay, so let me start with the introduction. Why do we want to do free energy calculations? And I want to give you some historical perspective. So the guy that you see here in the upper corner here is Bernie Alder. So Bernie Alder is considered to be the forefather of molecular dynamics. And he actually applied molecular dynamics back in 1957. So it was the first time to study liquids. And ever since then, it's been a race, or an unbridled race, for longer and larger simulations. And Yesterday, you saw glimpses of that in Emmad's talk, in Raphael's talk. So a turning point, I mean, as far as we're concerned in computational biophysics, a turning point for us was 20 years later, 20 years after Bernie Alder's first simulation. That was the simulation of Martin Karplus and Annie McCammon and Bruce Gellin. You have to put that, you have to journey back in time. I don't know if you guys are familiar with CCAM. So CCAM, this is European, stands for Centre Européen de Calcul Atomique et Moléculaire, talking Greek. So it's European Center for Atomic and Molecular Calculations. It still exists. They still organize workshops. It used to be in Paris at the time of the glorious France, now pretty much in the crapper. And now it's in Lausanne, where money is. But in fact, I mean, it's still distributed. I mean, there are various nodes where people organize workshops. But at the time when they had workshops, those were workshops for several months, and not just like for 2 or 3 days. And it's actually in Paris that these guys developed the framework to do the first ND simulation of biological system. And this biological system was BPTI, bovine pancreatic trypsin inhibitor, over 8 picoseconds in vacuum. At that time, that gave you a Nature paper. Of course, today you have to do a little bit more. But it was a major breakthrough at the time. And that really opened the door or paved the way to the kind of simulations that we see today. I mean, so yesterday you saw in Emmad's talk that you can actually simulate, or in Diego's talk that you can simulate this kind of system. So you have like this conflicting arrows or opposite arrows. So the larger the system, of course, the shorter the simulation. And this is the kind of architecture that you can, I think it's, okay. This is the kind of architecture that you need to simulate these systems. But what we are really interested in the context of free energy calculations, are the typical timescales of the collective motions, the collective movements that you have in systems. So Emad mentioned yesterday this transporter, this ABC transporter, that will, this motion that you see here, and this is to be put in the context of a membrane, this conformational transition, which is triggered by the binding of a substrate, occurs on the millisecond to the second timescale. This is the infamous villain headpiece, a short protein, or small protein, 47 amino acid. The folding is on the microsecond timescale, multi-microsecond timescale, typically 10 microseconds. This is the spontaneous binding of a small molecule, and that will occur on the nanosecond to the microsecond timescale. And of course, the spontaneous reorientation of water molecules will occur on the picosecond timescale. So you can see free energy calculation is some kind of a tweezer, a computational tweezer to act specifically on the various degrees of freedom of your system. So we use free energy calculations typically to study binding. I mean, I showed already this example. So for those who are interested specifically, this is Tamiflu binding to the neuraminidase of the H1N1 virus. Recognition and association phenomena, you can study protein. So this is protein ligand binding. You have protein-protein binding. Here you have conformational transitions. And here you have transport. So this is, this protein here is a tetramer. This is an aquaporin. So aquaporins are this family of membrane channels, not transporters, channels, that transport specifically water and very small alcohol. So in this case, this is the glycerol facilitator. And as you can see here, you have glycerol, and it's trying to get through this selectivity filter. It's a very cute protein. I mean, I even want to say an intelligent protein. So you have like this It's the selectivity filter that prevents anything smaller, no, anything bigger than water or glycerol to go through. So ions could potentially go through, but somewhere here below you have another filter that reverses the electric field to push back the ions outside back to the vestibule. So this is what you can do. I mean, this is what you have on the menu. These are like the things that you can, the problems that you can tackle with free energy calculations. So for that, I'm going to do another classification. We have methods that are based on histograms. And so what you're really doing is you define some collective variables that you are interested in. So I call them psi. That can be, for instance, the backbone angles of a peptide. And you're going to count the number of times you visit different values of psi. And then you can recover from this probability distribution, you can recover the equilibrium free energy. Then you have non-equilibrium work simulations. We heard about that yesterday. That's like pulling, and then, so then you get a work. But through this identity called the Jarzynski identity, which was put forth in 1997 by Chris Jarzynski, if you do this kind of operation, this kind of realizations many times, and there's a caveat here, you want to be in a near equilibrium regime, then you can recover the free energy. Then I missed the animation, but this is free energy perturbation. I'm perturbing the system, I'm transforming the system. This is an alchemical transformation, transforming one chemical species into another chemical species, and I can get the free energy through this. And finally, I can measure the force that is acting along a certain reaction coordinate model. So in this case, I had this little substrate going down this the gorge of this protein. And so I'm measuring the force exerted on this substrate, and I'm integrating the force. If I'm integrating the force, I'm getting the free energy. Okay? So don't be scared. This is just like the introduction. I'm going to go through each of these methods one by one. All of this is available in NAMD. So this is the phylogenetic tree of free energy methods in NAMD. Gives you like an idea of how much we have developed over the years since we started to implement free energy methods back in 2000. So like almost like 25 years of development of free energy methods. Now, a lot of these methods revolve around a module, an external module of NAMD called CoLVARs. You're going to hear a lot about CoLVARs, developed by Jerome and Giacomo Fiore. Now, let me address kind of the elephant in the room. You have a problem, and you want to know what's the best method for them. You saw that there are a lot of methods, and I'm just like touching the surface right now. If you want to know what's the best method for a given problem, and this is something that J.C. Gunbart, we'll hear from him tomorrow, and I worked on just as an illustration. So what you have here is the kind of like the bottom of the exit tunnel. This is the ribosome. You don't see the ribosome. The ribosome would be like all the way to the roof. And you have like the exit tunnel, the ceiling, sorry, not the roof. And you have from the exit tunnel, you have like in green, you have this peptide chain. And plugged to the exit tunnel of the ribosome, you have this protein, this channel called the translocon. And this is an important protein. It's found in the endoplasmic reticulum. And it's a protein that kind of decides if the nascent chain is a membrane protein, then the translocon will open laterally and let the peptide chain diffuse in the membrane, where usually it meets partners like a chaperone to fold. And so you have like a membrane protein. And if it's not a membrane protein, if it's a global protein, then the channel remains closed, and the peptide chain diffuses through the channel and undergoes partial folding by virtue of the hourglass-shaped channel, and goes on the other side of the membrane. One interesting question is, so experiment tells us that it's not that expensive to translocate charged amino acids like arginine, and people doing simulations were interested in this puzzling question: why is it so cheap to translocate an arginine? I mean, you would think intuitively that it would be way more expensive. So our colleague Toby Allen underwent back in 2007 a simulation whereby he would translocate one arginine attached to a pseudo-infinite polyleucine alpha helix. So the setup of the simulation is the following. So the idea is you have your pseudo-infinite alpha helix spanning the bilayer, and one of the leucine has been replaced by an arginine, and you're going to pull gently at equilibrium. You're going to pull gently the alpha helix upwards, so that progressively the arginine that's originally lied in the aqueous medium now goes into the membrane and all the way to the other side of the membrane. So if you calculate the free energy change, you start with 0. That's where you anchor your free energy. It's 0 when arginine is in water, and you end with arginine in water on the other side of the bilayer, so you should also get 0 with no hysteresis. And this is the free energy profile that you get, so mission accomplished. You start at 0, you end at 0. And you go through a maximum here, which corresponds to the free energy difference, or the differential solvation free energy for arginine. Arginine in water, arginine in the midst of the acyl chains of the bilayer. Now, I want to draw your attention to this. When you pull the helix upwards, you can see that the arginine doesn't go alone. I mean, charged arginine doesn't like to stay naked in a hydrophobic environment. So it comes with a retinue of water molecules to remain solvated. In doing so, it damages the membrane massively. So if you read the fine line of the supplementary information, then you realize that these people had to reconstruct the system periodically and restart their simulation to get the full free energy profile. Otherwise, you do too much damage to the membrane and you get garbage in the end. And we thought with J.C. Gumbart, maybe there is a smarter way to do this kind of calculation. After all, we're not really interested in this part. We are really interested in the free energy difference between water and the interior of the bilayer. And so you can rethink this problem from a different perspective. You can rethink the problem from an alchemical perspective. And so the kind of setup that we did is the same pseudo-infinite alpha helix spanning the bilayer and more than the bilayer. And then we have like these funky amino acids here that's where the C alpha carries 2 side chains. So you have like a carbon that has like 5 covalent bonds. You can do that when you do computational chemistry. Real life, not so much, but you can do that with the kind of alchemical transformation. We have a lot of parasite, I mean, noise.
Is it like
Maybe it's too loud. Let me see.
Is it microphone?
Maybe I don't need the. Do I really?
Excuse me.
Do I need this, or do I need this for Zoom, or you can hear me? Okay, let's get rid of this. Sorry.
No.
Is it bad?
Oh, we're running out of battery. That's why.
Ah, Okay.
Make sure you can
Yeah,
go down
let me
to it.
continue. So, so you get the kind of setup that we did, right? So we have this special amino acid, and I will explain to you how we do that, that carry two side chains at the same time, an arginine and a leucine. And the thing is, when we transform the leucine into arginine in the water phase, then we do the reverse transformation in the membrane phase, meaning that we always have the same net charge, okay? If you do that, you get the result of Toby Allen, nothing more. Still doesn't explain why by experiments you measure 2 to 3 kcal per mole for why it's so cheap, where you have this compression of the so-called hydrophobicity scale. Now you have, if you really want to explain why they get 2 to 3 kcal per mole, then you have to invoke another partner, which is the translocon, and which provides a hospitable environment for an arginine. So it's not a direct translocation of arginine, it's translocation of arginine through the translocon. Having said that, I'll go directly to alchemical transformation. That's like a natural transition. Yes.
In the previous system, would it also be important to consider that inside the membrane, the dielectric constant is lower, so there's a possibility of change in the protonation state of the arginine?
That's a very good point. And in fact, we expect to have a pKa shift when, so you can do actually, and I'll mention that briefly. One of the applications of French calculations is to do constant pH MD. And of course, there's a chance that we've done it for, sorry, thank you. So we've done it for other amino acids. We've done it for glutamate and for aspartate, going through the membrane, thank you. And you can see the pKa shift. You can see the change of protonation state. So you start with your glutamate in the context of a tripeptide, I think, or a pentapeptide. I forgot exactly what we did, but you start with, so the pKa is about 4.7, if I remember correctly, for glutamate. So naturally, when you are in water, it's charged. And when you enter the membrane, then you can see that it becomes protonated. Now, I'll show you now at the end of this chapter. But yeah, very good point. Problem with my pants, sorry. Okay, so let me start with, again, some historical context. So these guys are considered to be the forefathers of alchemical transformations. On the top is Bill Jorgensen. First really meaningful alchemical transformation with Ravi Mohan in 1985, so almost 40 years ago, transforming methanol into ethane with a remarkable accuracy at the time. Followed shortly by Peter Coleman. Peter Coleman, so if you're not familiar with Bill Jorgensen, this is the TIP3P guy, this is the OPLS guy. Peter Coleman passed away in 2001. He was the father of Amber, the Amber force field, the Amber program. And this is Herman Berenson, also passed away. This is the father of Bromos. He's also one of the trailblazers of free energy calculations. I think he did, yeah, 1982. This was not exactly an alchemical transformation. It was more like calculating the free energy cost of creating a cavity in a liquid. And you know that this is important because solvation, when you do solvation free energy calculation, or the solvation process in general, is first creating a cavity in a liquid to accommodate the substrate. So calculating the reversible work to push the solvent molecules around to to insert the substrate. So Bill was actually the one who actually developed the framework that we are still using today. And the framework that he used was called the single topology paradigm. So the single topology paradigm, you're trying to find, so you want to transform A into B, one chemical species, into another chemical species. And you're trying to find the common denominator between the two. So in this case, well, did I miss the, maybe I need to replay the, yeah. So I'm transforming this OH into a CH3. And so the common denominator will be the CH3 because it's bigger. And so what you do in the single topology paradigm, once you have found your common denominator, then you're going to perturb all the parameters of your topology. So you're going to change the charge borne by the carbon into the charge borne by oxygen. You're going to change the van der Waals radius of your carbon into the van der Waals radius of an oxygen. And what about these guys? Well, they are dummies, so they are kind of dangling on this atom, right? And so if you start with OH, so you will have an OH with two dangling hydrogens, and then you make this hydrogen come to life. So they kind of ghost, they don't interact with anything, and then you grow progressively your hydrogen radii. You need to adapt, of course, the bond length because you're going from a CO bond to a CC bond, so 1.4 to 1.55. And you need to correct for that. And usually the way we proceed is we do electrostatic decoupling, meaning that you make your van der Waals parameters grow first before you grow your charges, because you don't want to have naked charges, which is conducive to instabilities in your trajectories. And shortly after that, Martin Karplus and his group proposed an alternative to that, which is called the dual topology paradigm. So in the case of the dual topology paradigm, which is exactly what I mentioned previously, remember this alpha carbon bearing two side chains that do not see each other. So when one is interacting with its environment, the other is kind of a ghost. And so this is what we have. So we are defining at the same time two topologies. And when one disappears, the other appears. So this is the animation. So I'm making this OH appear at the same time as this CH3 disappears. They are present, I mean, through the files, to the parameter files, to the topology files, they are present, but they do not see each other, whether directly or indirectly. By indirectly, well, directly would be like through non-bonded interactions, but also indirectly through valence angles. So imagine that I have two side chains. I cannot have a C beta, C alpha, C beta parameter. Right? Makes sense? Same thing for the dihedrals. And all of this is controlled through an exclusion list. So when we define this guy, there is internally in NAMD, there is a little code that's called alchemify. So you define your dual topology, and it will be a dirty PSF file. And alchemify will clean up that in the background, removing all the unnecessary interactions. Yes?
Is there an explicit solvents in this case?
Yeah. There is a, so when I say that the side chain, so we have like the two side chains that do not interact with each other. They don't, one of them interacts with its environment. The other doesn't see the environment and is not seen by the environment. And at some point when I start doing my simulation, then my transformation, then the other side chain appears, starts to interact with the environment at the same time as the alternate topology fades away. And all of this is controlled by a general extent parameter or coupling parameter lambda. So in the previous case, in the single topology paradigm, I told you that we are playing with the non-bounded parameters. So what I'm saying is that the charge at lambda is equal to lambda times the final charge plus 1 minus lambda, the initial charge. And the same thing for the parameters, the van der Waals parameters. Here, I'm perturbing directly the interaction energy. So the interaction energy is also a linear function of the interaction energy in the initial state and the interaction energy in the final state. Make sense? So in one case, I'm playing with the parameters of the force field. In the other case, I'm playing directly with the potential energy function, right? One thing when you build this dual topology, you need to take care about branching. So at what point do you branch out? So when I define your alternate topologies, your alternate states, so where do you branch these two topologies? So for that, you need to do a calculation of the charge distribution, usually with quantum mechanics, right? You can fit charges to the potential, or in the charm force field, you fit the charges to the interaction energy with a water molecule surrounding the molecule. But as you can see here, it would be a bad idea to branch the two topologies at the level of this carbon. And the reason is, if you look at the charge distribution, you have a charge of minus 0.18 and a charge of plus 0.05. And that is due to the fact that you have this electron withdrawing group here. And so it's kind of sucking the electrons in that direction. And so this is depleted, right? And so it would be advisable to branch maybe at this level, one carbon above, and keep that as a common denominator between the two topologies. Okay, so now we have the single topology paradigm, we have the dual topology paradigm, so we know how to transform one species into another species. What do we do with that? And we calculate the free energy. So more pictures, more names. So this is Lev Landau, and this is Bob Zwanzig. It's interesting how history, makes name disappear. And oftentimes when we talk about free energy perturbation, we only think about Zwanzig. But the seminal ideas of free energy perturbation were actually planted by or devised by Lev Landau as early as 1938. But they're both considered to be like the forefathers of the of free energy perturbation, which is embodied in this equation, which relates the free energy here to the potential energy, actually to the perturbation term. So that's the difference. Delta U is the difference between the initial state and final state of the transformation. And this thing here is an ensemble average with respect to 0. So I'm going to use this convention. 0 will be my initial state, and 1 will be my final state. So the beauty of this expression is that I only need to sample the initial state to infer a free energy difference between the initial state and the final state. And so delta U, as I said, is a linear combination of the final potential energy function an initial potential energy function, U0 and U1. It's a formally exact for any perturbation, provided that you can sample infinitely. And it's an important sampling method. I want to draw your attention to the use of the vocabulary, important sampling, enhanced sampling. In general, people think about important sampling when you sample important region, when you focus your sampling to important region. And enhanced sampling when you try to achieve ergodicity, meaning that you are gonna visit everything. I mean, the entire configurational space. We're gonna talk about that. So how do we do in practice? Imagine that I'm interested in the differential solvation free energy of two ions, let's say lithium and rubidium. The only difference is the ionic radius of these two species. So I'm going to start with lithium in water. That would be my U0. And I will generate a long trajectory with U0. That will give me my ensemble average over state 0, over the reference state. And for each snapshot, for each configuration, I will calculate what delta U is, okay? And so, I need to calculate U1 as well. So I get my delta U. And once I have that, then I can calculate my exponential of minus beta delta U and average that over the entire trajectory. And that will give me, in principle, my free energy. It's not so simple, because even though those are like two small ions, monovalent ion, it's still a pretty big perturbation to go from lithium to rubidium. Remember that I'm thinking in terms of U0, meaning that transforming lithium to rubidium will generate a lot of clashes with the surrounding solvent, right? So you need to take that into account. And probably what you will have to do is proceed through small increments of the transformation. The equivalent of free energy perturbation formally is thermodynamic integration, which was proposed by John Kirkwood, also back in the 30s. And so it's a rewriting of this perturbation formula in terms of an integral. And so what we calculate here is a derivative of the potential energy with respect to this coupling parameter that takes me from U0 to U1, from state 0, from the reference state to the target state. You can see that as a force, actually, if you think of lambda as a coordinate, as a Cartesian coordinate. And then we go to the concept of potential of mean force, because this is a potential energy, and you derive that with respect to a coordinate. So you get a force. It's average potential of mean force. Okay, so how do we deal with large perturbations? And I assert that going from lithium to rubidium is already a large perturbation. So this guy here is John Vallow. The name may not ring a bell, but Vallow and Torrey, 1977, umbrella sampling. If you have heard the name, it's one of these important sampling methods for geometric transformations. What he proposed earlier than, actually 5 years earlier than umbrella sampling, is a method called staging. Staging means that you're gonna chop your simulation into sub-transformation. Why do we do that? Well, let's rewrite the perturbation formula, introducing here a probability distribution, the probability distribution of finding, of being at a certain value of delta U, right? And let's further assume that this probability distribution here, so this is probability, my perturbation formula now is expressed as this integral here. I'm integrating over delta U's, and I have this histogram here of delta U's, different states that I'm visiting having a certain energy delta U times the Boltzmann weight, okay? And now imagine that we are in a perfect world where everything is Gaussian. I would love to live in that world. And so my P0 delta U is this guy here, okay? And so when you multiply a Gaussian function by an exponential, you get another Gaussian function that is shifted to the left. And so this is my product here. And it's shifted to the left by 1/2 of beta sigma square, sigma being the variance of my histogram, okay? So now you can see that the larger the perturbation, the larger the sigma, the greater the shift to the left. But when I do that, now you can see that if I compare P0 delta U and the product of P0 delta U times the Boltzmann weight, part of this Gaussian function lies in a region where I don't have any statistics. Because what I really have sampled is this region, right? So here I have no information. That will be the error that I do on my free energy estimate. Because I've not sampled anything here. My sampling stops here roughly at minus 0.6. Get it? So how do I remedy this? Well, John Vallow, I stratify, I stage my simulation, I stage my transformation, and I introduce intermediate states so that my ensemble, my configurational ensemble nicely overlap. Okay? And so my free energy, my total free energy will be a sum of individual free energies. Okay? So instead of going directly from 0 to 1, I'm going to 0 to, let's say, increments of 0.1, so 0 to 0.1, 0.1 to 0.2, 0.2 to 0.3, and so on and so forth. And I'm just adding the free energies for this incremental transformation. I want to draw your attention to this. These are the so-called Gibbs-Bogoliubov bounds. Those are the bounds of the free energy. So the free energy is less than the average of the potential energy with respect to 0, and is greater than the average of the potential energy with respect to 1. So that would be, if I were doing a simulation with 1, with the target state as the reference, and this is when I do the free energy calculation with 0, with the initial state, the reference state as the reference, okay? Then it kind of begs the question, how many strata, how many intermediates do I need to get convergence? So here is a simulation of a very simple transformation. This is a neon atom in a box of water. And I'm staging in 4 windows. And I will tell you a little bit about that in more detail, but it's good practice when you do these calculations to verify that you satisfy micro-reversibility. And to verify that, meaning that if I go from 0 to 1, and if I go to from 1 to 0, I should get the same free energy with a sign, right? If I don't, there's something wrong. It also means, as a corollary, that I should have a nice overlap of the distributions that I'm, or the distributions that I'm sampling. So my P0 and my P1 should nicely overlap. because I have sampled the same ensemble of configurations? Well, as you can see here, so I've done the forward and the backward, the forward and the reverse simulation. And I've done that for the 4 windows. So typically here I'm going from 0 to 0.25, 0.25 to 0.5, 0.5 to 0.75, 0.75 to 1. And I'm doing a crappy job because my probability distributions don't overlap at all. Best case here is that the last window by sheer luck. So clearly, this is not the best stratification strategy that I have chosen. By the way, I'm going to put occasionally the NAMD lingo when you do these simulations. What would be the command line in your configurational file, in your in your configuration file? So we're using a little script called fep.tcl to drive this free energy perturbation calculations. And so you have this keyword run FEP. And so if you write 0.1.0625 n steps, it means that you want to go from 0 to 1, lambda equals 0 to lambda equals 1, with increments of delta lambda equals 0.0625. If you divide 1 by 0.0625, that's 16. So it means that you're using 16 windows. And for each window, you're running n steps. And you define above what n steps should be. So 4 windows, bad. So now I'm moving to 16 windows. And lo and behold, now, if I'm using 16 windows, I have a much better overlap for each window between my forward and my backward transformation. And now I can be more confident in the free energy estimate that I'm getting. It's not perfect. I mean, I agree. Like usually the first windows are the culprits. And there's a reason for that, because in the first window, this is when you make the alternate topology appear in the solvent. So it's prone, even though we're using tricks, I'm going to mention that, to remove the singularity due to possible clashes with the solvent. We remove that by something called soft core potentials, but still, the first windows are usually problematic. So that's why there is a little error here, but it's not so bad. It's not so bad. So 16 windows is actually quite acceptable. Okay, so in practice, how do we deal with that? So in NAMD, we're still doing things kind of the old-fashioned way by default. We proceed sequentially. We go from 0 to 1 sequentially. But if you have access to a host of computer nodes, GPUs, and the like, nothing prevents you from distributing the task across these different nodes. What we do in NAMD, and then that's kind of the history of NAMD, is to do well on large arrays of computer nodes. And so we use for that domain decomposition. So domain decomposition means that we're splitting the simulation cell into patches, a large number of patches. Usually we put a lot of patches on one compute node. But what you can imagine, so this is what we're doing here, we're distributing these patches, but you can actually imagine on top of that, having, and so traditionally, we use these different nodes to handle one value of lambda. But if you have a large number of compute nodes, a large number of GPUs, you can run in parallel the different values of lambda. Nothing prevents you from doing that. Of course, you need to prepare each simulation, have like properly equilibrated. That's vital. And in fact, you'll see this afternoon when you play with this in the tutorials, every time you change lambda, So you go from lambda 0 to lambda equals 0 to lambda equals 0.1, and then lambda 0.1 to 0.2. You need to re-equilibrate. And the reason is that you want your system, when you start with lambda equals 0.1, say, you want your system to reflect this value of lambda equals 0.1. You don't want to have a kind of a memory effect, which is sometimes referred to as Hamiltonian lag. You don't want to have that. You want your ensemble of configurations to reflect the actual value of lambda. Otherwise, if your system is you want to simulate, let's say 0.6 to 0.7, and your system is still lagging behind and reflecting, let's say 0.4, this is prone to catastrophe and to large errors in your free energy estimates. So you need to properly thermalize, properly equilibrate to reflect the actual value of lambda that you want to simulate. And so, yeah, so you can, we have the capacity to, I mean, we have the tools to simulate at the same time the different values of lambda. And then you need to broadcast this at the end to get your final your net free energy estimate going from 0 to 1. And we even have like options to swap values of lambda to do like some kind of replica exchange. I'll mention that in passing. Is this clear so far? Yeah?
These simulations don't have to talk to each other.
If you simulate the different values of lambda independently, no, they do not have to. They do not have to talk to each other. If you start doing what we call Hamiltonian hopping or lambda replica exchange, then of course they need to talk. But we have in NAMD, we have a multiple copy infrastructure to do all this simulation, like multiple walkers, replica exchange. Yeah. Okay, so I mentioned to you before that it's good practice to do forward and backward transformation, just to check that thermodynamic micro-reversibility is properly enforced or properly verified. But there is another advantage of doing this, and this is yet another picture, and this guy is Charles Bennett. And Charles Bennett in 1976, Charles Bennett from IBM, nothing to do with statistical mechanics. I think that probably there was a side project. The guy works on quantum teleportation. But in 1976, well, he proposed this, a maximum likelihood estimator of the free energy, harnessing the statistics that was accrued in the forward and then backward transformation. And so this is what we call bar in the free energy lingo. So you have to solve this set of equations. Please note that you don't know what delta A bar is, neither do you know what this coefficient C is. But what you can do is you can prime the process, prime this. So this has to be solved self-consistently, but you can prime the process, replacing delta A bar by the FEP estimator. And this is what we do, in fact. So I'll show you. We have this available in VMD to post-process your free energy calculation. So you're gonna solve that. The code is going to solve that. The plugin is going to solve that for you. Feeding delta A FEP to start the solving these equations. Then, of course, from the forward and the backward forward, that's the number of snapshots in the forward, that's the number of snapshots in the backward. You're gonna get your bar estimator in a few iterations. And the good news is these people here, Han and Ven, they've cooked the statistical error that is associated to the bar estimator. So we have a statistical error, or the variance, associated to the FEP estimator and to the bar estimator. One thing that you can do if you're really cheap, and that goes back actually to Bill Jorgensen. Bill Jorgensen in 1985 had figured it out. I mean, it's quite amazing, in fact, that all the tools were there in that particular paper, 1985. And at the time, I mean, computing was very expensive. And if you read, or if you had the chance to talk with Bill, he will tell you that when he did this first transformation of methanol into ethane, they had to make an executive decision of like investing on this problem, and the others were kind of crossing their arms, sitting on their hands, waiting for the results to be obtained. So it was like a month of calculation on their computer. At the time, he was at Purdue in West Lafayette. And but to make the calculation cheaper, he came up with this idea of double-wide sampling, meaning that at a given value of lambda, you're calculating the forward change and the backward change at the same time. It's a little bit cheaper than doing forward all the way, backward all the way. It's a little bit cheaper. It's not half cheaper, because you still have to do 3 energy evaluations. The evaluation for this value of lambda plus delta lambda, of lambda minus delta lambda, which is still cheaper than doing like all the way in one direction and all the way in the other direction. And that we have also in NAMD, if you're interested. And so I was mentioning that we have, so these are the many plugins that are available in VMD. And so one of them is called Parse FEP, which you have here. And so Parse FEP will do the post-analysis. So if you do free energy perturbation with NAMD, you're going to get the FEP estimator. That's what you get. But if you've saved enough data, you can decide that. I mean, there is a keyword for that. You can save like every step. You can write every step your potential energy going forward and going backward. Then you can calculate this other estimator, the bar estimator. You can also look at all your distributions, forward and backward distribution, and just see, visually assess the quality of your free energy calculation. You can look at the overlap of your potential of your probability distribution. You can also look at the time series of your free energy, of the net free energy change as you accrue sampling, right? I mentioned endpoint catastrophes. So when you make your alternate topology appear in your simulation box, there's potential clashes with there are potential clashes with the solvent molecule, meaning that the topology will appear in a locus that is already occupied by solvent molecules. And if you don't do anything special, this is conducive to crash of NAMD, because it's like you have like these huge van der Waals energies. So Annie McCammon, again, and Wilfried van Gunsteren proposed a rewriting of the van der Waals potential when you do free energy calculation. And you can see that it involves lambda, and it involves this parameter here, kind of a shift parameter. So basically what you're doing is you're kind of shifting your van der Waals term. It does not affect the net free energy change. It's just like shifting just a correction, if you will, of this potential to avoid clashes with the surrounding solvent molecules. And this is controlled in NAMD. This is controlled by Alk van der Waals shift coefficient. And you can see, you can verify for yourself that if you play with this parameter, it does not change the actual net free energy change, but it saves you from or makes you immune to crashes of NAMD, trajectory instabilities. In the old days, what we would do is we would proceed with different increments of lambda. So we'd use like 10 to the -6, 10 to the -7 at the very beginning, just to prime the simulation, like just to push the water molecules around. But with that, you don't need to do it anymore. So you can start immediately with, you can use a constant value of the increment. In practice, so what do you need to do these calculations? Well, you need an equilibration simulation. That's the preamble of doing a free energy perturbation calculation. So meaning that you need Cartesian coordinates, velocities, extended system, properly equilibrated configuration. So that's, if you're not familiar with NAMD, I mean, this is the size of the box, the velocities, and the coordinates. Then you need an ALK file. So what's an ALK file? An ALK file is a clone of the PDB file, but wherein you have changed either the X, Y, Z occupancy or beta column with flags to tell NAMD what are the atoms that are appearing, what are the atoms that are disappearing, what are the atoms that are left unchanged. Left unchanged, 0, appearing +1, disappearing -1. Okay. Then, of course, you have the PSF, and I told you that you can use a dirty PSF, doesn't matter, because it's going to be cleaned by NAMD internally. Then your usual NAMD file with the proper lines, the proper keywords to control the FEP calculation. And you're going to get, in addition to the traditional log file, you're going to get an FEP out file, which contains all the statistics to do the post-treatment. Like we are dumping the potential energy forward, backward, and the net free energy change. All good? Yes?
The PSF, so if you're changing, let's say, VP into VDM, I mean, the parameters are very different for the VDM and lithium. I mean, you just start with lithium and somehow the parameters are gradually morphing into the VDM.
Yeah. Yeah.
You represent that in the PSF?
Well, actually, the parameters are not in the PSF. What you have in the PSF is the charge. The charge is constant. Lithium and rubidium is +1. It's actually taking the parameters from the one of the PAR files, which has like the van der Waals radii. But it knows that it has to transform actually, remember that we are in the dual topology paradigm. So we're not transforming the parameters per se, as we would do with the single topology paradigm, where the van der Waals radius would be a linear function of its initial value and its final value. But we are transforming directly the potential energy function. So the interaction energy between lithium and water and the interaction energy of rubidium and water.
So both parameters should be available in the parameter.
Yeah, it's in the PAR file. Yeah, you don't need to touch anything there. The only thing that you have to worry about is your dual topology when you actually have a dual topology. In the case of two ions, there's no real dual topology. So you can, it's a good practice actually if you do that to improve convergence, is to impose a slight restraint on the ion, on the position of the ions, to make lithium overlap with rubidium. Instead of having like two cavities at two ends of the box, two edges of the box, You put like a little restraint which will not participate in the free energy change, but it just makes sure that the lithium overlaps nicely with the rubidium. Any other question? Yeah.
Is it practical to define a compound of lithium dummy rubidium as a dual topology?
But again, I mean, dual topology really would make sense when you have something bigger and when you have like a common denominator. And in this case, there is no common denominator. But yeah, I mean, you could potentially imagine all kinds of transformation, like transform the lithium into a dummy particle without a charge, and then transform like this dummy into a rubidium without a charge, and then make the charge appear. I mean, you can imagine. I mean, keep in mind that, and I didn't say that, but didn't want to insult you, but free energy is a state function, so you can think of any pathway you want. Ultimately, you should end up with the same free energy change. But always keep in mind the, when you want to do these calculations, it's always good to draw a little thermodynamic cycle. We're going to see a few in a minute, but you want to keep in mind the thermodynamic cycle that you actually want to simulate. Does that make sense? Right? Always plan ahead what you want to simulate. So here's an example of, this is actually the first exercise that you will do this afternoon. I'm transforming ethane into ethane. It's really a stupid transformation. But the virtue of this transformation is you know what the answer should be, hopefully. So it should be 0. And the way we define that in terms of dual topology is a pseudopropane. So this is a pseudopropane, and the common denominator would be like this thing here. And then the idea is like to make this group vanish as this group appears. So you can see that when I say pseudopropane, it's kind of a superimposition of 2 ethane molecules, but with like this part here that just stays. That's my common denominator. And so this is what you should get. This is what we obtain with the soft core potential. I think that the tutorial also asks you to do the simulation without the soft core correction, just to see, the effect of the soft core, and that you're better off simulating always with the soft core. But that was a quick and dirty simulation, and you can see that you converge very quickly to the correct answer. You should get 0. And you should get 0 with a very small hysteresis, which actually provides you a good estimate of the error on your free energy calculation. If you calculate the hysteresis between the forward and the backward transformation, ideally it should be 0, but that would give you an idea of the error on your simulation. Yeah, so one thing that's, so you remember that what I mentioned for the single topology paradigm, we also have a similar thing for the dual topology paradigm, decoupling electrostatic and van der Waals. Remember that you would never want to have a naked charge in your simulation box, because then if it has no van der Waals, then it will clash, it will move very fast and clash with other atoms. So when you make a particle disappear or you make a particle appear, you always want to have your van der Waals term ahead of the electrostatic term. So you can see here, I have like this 4, so I'm doing like a dual transformation. So I'm making a moiety appear at the same time as I'm making another moiety disappear in my molecule. And this is controlled by these 4 values of lambda, these 4 curves for lambda. So I have my van der Waals disappearing, my electrostatic appearing, and my van der Waals appearing, and my electrostatic disappearing. So if I just take like the van der Waals and the electrostatics disappearing, you can see that my electrostatic disappears much faster than my van der Waals. Again, because I don't want to have any charge naked. And for the electrostatic, I want to make my van der Waals appear before my electrostatic, and it's also reflected here. And so you can have like this scheduling for outgoing particles and incoming particles. And so this is controlled by these two keywords, alk van der Waals lambda end and alk electrostatic lambda start. So you can see that you can verify. So if you have like 0.7, so for outgoing particles, the electrostatic starts at 0 and ends at 1 minus this. So that will be like 0.3. So as you can see, so the electrostatics, so outgoing particles, so that would be what's, oh no, that's van der Waals, sorry. So van der Waals, 0.7, so that will be, so we start at 1 minus, okay, so we start at 0.3, and then we end at 1. So this is exactly what it is. So we start at 0.3, so it's maximum potential at, so 1, and then at 0.3, we start decaying all the way to 1, okay? And for the electrostatic, we start at 0, and we end at 1 minus 0.5, which is 0.5. So we start at 0, and we end at 0.5, and then it's 0, okay? So always keep in mind to be ahead in your scheduling, be ahead. Van der Waals should be, you should always have more van der Waals than electrostatics, okay? What about entropy? So far we've talked about free energy, but can we get the entropy for the same price? What Martin Karplus proposed back in 2004 was a rewriting of the 20-Landau formula applied to entropy. So this is a perturbation formula. But as you can see, so it basically, this formula comes from the simple expression of delta G. Delta G equals delta H minus T delta S. Should I mute it?
Yeah, just mute it. You can check it later.
How do you do that? Oh, it's fine.
It's not the battery's full. That's not a problem. I don't know.
Maybe after a while it's...
Yeah. Or maybe turn off and turn on again then.
Yeah.
Just lock. Okay, there's one way to unlock it.
Yeah.
Well,
Okay. Yeah. So yeah, you take your the expression of the free energy, either the Gibbs free energy or the Helmholtz free energy. Let's say the Helmholtz free energy. Delta A equals delta U minus T delta S. And you plug in that, the expression for delta A, you plug in that the expression of the perturbation formula. So, with the ensemble average of exponentials minus beta delta U with respect to state 0, with respect to the reference state. And you obtain this. Now, the main difference with the perturbation formula for free energy, the perturbation formula for free energy is essentially dealing with delta U. It's an ensemble average or an exponential of delta U. Now you have here something more complicated. You have an ensemble average of directly U0. And that's going to take way longer to converge. In the perturbation formula, the Zwanzig formula, you're dealing directly with the perturbation term. the difference between, let's say, state 1 and state 0. But here you're dealing in U0, you have everything. You also have your solute solvent and your solvent interactions. So that's going to take a while to converge. And in fact, so this is an example of the hydration free energy of ethanol. And what I'm showing here is the evolution of the free energy, of the internal energy, and of the entropy, so T delta S. As you can see, as early as 8 nanoseconds, my hydration free energy has converged. It's not going to change. Dashed line is the experimental value. Solid line is what I'm actually measuring. So it's just like reflects the uncertainty from the force field. But this is converged. I mean, as early as it actually converged even earlier than that. It takes a long while actually for the entropy and of course for the internal energy is the same to converge to something meaningful. Actually, I would say that maybe like 10 times longer, possibly even more than the free energy. Another way to get the entropy, and this is Ron-Levy here, is to use this identity. This is actually annoying. I'm going to stop this.
Let's stop later.
Actually, it's blinking. I'm not sure why it's blinking, but it's okay. Yeah, it's fine.
Yeah.
Let's not worry about it. Okay, so this alternate route here, so this identity, so it's the derivative of the free energy with respect to temperature at number of particle in volume constant. We're going to think of that in terms of finite differences. And so the way we approach this problem is we're running simulations at different temperatures. And we're getting the free energy at different temperatures. And so, and then we calculate the delta S based on this simulation at different temperatures. Let's say that you simulate at T plus delta T and T minus delta T. And so you have like delta A at T plus delta T and T minus delta T, and you divide by 2 delta T's. Now you have to be really careful about the choice of delta T. If you're taking something that is too big, then you're no longer in this finite difference approximation. If you're taking something too small, then the difference in free energy between T plus delta T and T minus delta T is within the error bar of the simulation. So the choice is very critical, but it works. It works. One of the exercises that you'll have to do is calculate a hydration free energy. How do we do that in practice? Remember what I was telling you? Always draw a little thermodynamic cycle. So when you think about hydration or solvation process, you think of the horizontal transformation. So you have an ethanol in vacuum, and you bring it reversibly into water. And that will give you the delta G, the free energy change, delta G of hydration. Now we are talking about alchemical transformation. So we're going to think about this problem through the prism of alchemical transformation. And so we're going to make the ethanol disappear in the vacuum on the left-hand side. And we're going to make the ethanol disappear in the water phase on the right-hand side. And so this minus this is equal to this, because of course, transforming nothing into nothing is 0, right? So this is the setup. So I have my ethanol in bulk water. I have my ethanol in vacuum, and I'm making them slowly disappear using lambda, using a schedule. And there you go.
they're gone. Why do I need to complete the full thermodynamic cycle? So this is in reference to a keyword that is still in NAMD, and that should be in NAMD, but it's still in NAMD, called alk decouple. So alk decouple gives you the possibility to skimp, to not do the full thermodynamic cycle. And this is something that you should not even consider. Always leave it off. If you put it on, it implies that the intramolecular, the intra-perturbed molecular interactions are the same in the gas phase and in the aqueous phase. And that you can make the economy of not simulating the gas phase. Nothing could be further from the truth. I want to remind you, so that it's completely clear for everyone, on Zager's law, that the electrostatic terms of the free energy depends on the square of the dipole moment of the molecule. So it means that in the gas phase, when epsilon equals 1, the molecule will have a tendency to adopt a conformation that minimizes the dipole moment, where I'm talking about like a flexible molecule. Whereas in the water phase, where the dielectric is equal to 78.4, will have a tendency to maximize its dipole moment. So if it's a very flexible molecule with very distinct conformation in the gas phase and in the water phase, we're going to have very different conformations and therefore very different intramolecular contributions. So you cannot make the economy of not simulating the gas phase and the water phase. So it's good practice, ignore this keyword, leave it always to on, off, okay? I know it's I hope that I didn't blunder and made myself clear. I mean, it's important that you ignore this keyword because intramolecular interactions can be very different in the gas phase and in the water phase. So again, so when you do these calculations, forward and backward, then you do bar, this is what you get. So forward, backward, that will give you an ID. So very small hysteresis. This is the bar estimator minus 4.4, experiment minus 5.1. Yes, I mean, this is sucks, but this is what the force field gives you. Keep in mind that we're dealing with non-polarizable force field. We're ignoring induction effects. Force field is not perfect. I mean, it's not bad. I mean, we are like within chemical accuracy, within KT from experiment. But that's the kind of number that you should expect. Let me say a few words before the break about protein ligand binding, because I'm sure that some of you are interested in this. It's usually considered to be easier to deal with relative binding affinity than absolute binding affinity. By relative, I mean like we're comparing two ligands. This is what we have here. Or we're comparing two hosts. This is what we have here. So if we're comparing two ligands, what experiments will give you for this equilibrium, protein plus ligand A gives protein bound or ligand A bound to protein. You get that from ITC, for instance, isothermal calorimetry. You get that from Biocore or SPR, so surface plasmon resonance. They will give you the binding constant and therefore the delta G. What we do from an alchemical perspective, is we transform the ligand in the bulk state. So in the absence of the protein, because the protein doesn't change on the left-hand side. So you can just have a simulation with only the ligand, and you transform the ligand from A to B. And here on the right-hand side, you do the same thing, but in the presence of the protein, in the binding pocket, which means that you need to have the binding pause of the ligand bound to the protein. In this thermodynamic cycle, we do something a little bit different. We have protein A, it's the same ligand, but the ligand can be bound to the protein A and to protein B. Typically, what I had with neuraminidase, Tamiflu binding to neuraminidase, same ligand, but I was simulating the wild type neuraminidase, and I was simulating a mutant of neuraminidase, a mutant, so because the virus evolves, and at some point the virus makes itself immune to Tamiflu, and then the virus continues to propagate. Right? One amino acid is enough. Boom. The virus is no longer affected by Tamiflu. So it may or may not require geometric restraints to do this transformation. And this is well suited, I mean, especially this, well suited to congeneric compounds. You don't want to transform, especially with dual topology, you don't want to transform compounds, I mean, molecules, substrates that are very different. Now, if we're, yes. Yeah.
One base. Okay.
And got very highly. That's right. And we did not get good convergence with dealing with this there.
You might, yeah, and it's very flexible. That's the problem. It's super flexible. You might need to add restraints for that, but then you need to choose carefully how you apply these restraints. I'm going to say something here. Maybe we can talk in private. What? 2 minutes? Okay, so I have to. Yeah. Thanks. So let me just, before we go to the break, talk about how do we think about absolute binding free energies. And so this guy is Jan Hermans. He's actually the trailblazers in this area. One thing that you want to worry about is what we call the floating ligand problem. The animation is gone, but so the idea is that, you know, I told you when you do this free energy, this alchemical transformation, you transform the ligand into nothing. So as it's transformed into nothing, meaning that you have annihilated the interaction energy between the ligand and the protein, the ligand starts to float around because there's nothing like to attach it to the protein, right? And so it's floating around, you know, living its happy way, drifting away from the protein. But now you think about the reverse transformation. There's a snowball chance in hell that it will reappear at the binding site. So you need to address this. And the way to address this is by, you know, adding a set of restraints. And so what you will do is you will rewrite or recast your equilibrium, your thermodynamic cycle. So ligand 0 would be the unrestrained ligand, and you would add some restraints to fix it, to prevent this thing from happening. So you will restrain it at the binding site, and COP stands for conformational, orientational, and positional. And any restraint that you add in the binding site, you also have to add that in the bulk, right? And so now you have a constraint, or sorry, a restrained ligand, actually, oops. Restrain, constraint. Then Namely uses the keyword constraint when actually they mean restraint. It's explained in the manual, but yeah, there's historical reason. So we are restraining, meaning that we are applying harmonic potential to enforce a certain orientation, a certain position, a certain conformation. Constraining would mean that, or using the word constraint means like we're actually removing a certain degree of freedom. We're talking about holonomic constraints. That's what you have in shake, rattle, when you're actually constraining physically the geometry of the molecule. Okay, and so then only when the ligand is frozen, then I do my alchemical transformation in the bulk and in the binding site. And then you need to do the bookkeeping to add up the various contributions that come from the restraint. Because I mean, if you're restraining something, it means that it's a loss in configurational entropy, right? Which contributes to the free energy. So you actually, in a sense, you're biasing the free energy calculation. So you need to account for these restraints that you're adding and the reversible work that they correspond to in your binding free energy. So you need to calculate. So you're adding restraints, but you need to calculate the contribution of this restraint.